Have you ever noticed how things seem to get bigger when they warm up? This fascinating phenomenon, my friends, is called thermal expansion. It's all about the dance of molecules. Imagine tiny particles constantly jiggling and vibrating. These are the molecules that make up everything around us. As we heat something up, we give these molecules more energy. They jiggle faster, bump into each other with more force, and need more space to move around. This increased movement and spacing of molecules makes the object expand in size. Pretty neat, huh? Thermal expansion is a fundamental concept in physics, and it plays a crucial role in our understanding of how the world works. Now, how do we measure this heat that causes expansion? Enter the trusty thermometer, a device we've all encountered at some point. Thermometers rely on the principle that certain materials expand or contract predictably with temperature changes. One type is the liquid in glass thermometer, where a liquid like mercury or alcohol expands within a narrow tube as the temperature rises. The higher the temperature, the higher the liquid climbs. But how do we decide what temperature a certain height corresponds to? That's where temperature scales come in, like Celsius and Fahrenheit. These scales define specific reference points, like the freezing and boiling points of water, allowing us to assign numerical values to different temperatures. So the next time you check your temperature, thank the clever invention of the thermometer. We've talked about heat and temperature, but what about the transfer of heat? That's where calorimetry comes into play. Calorimetry is the science of measuring heat flow during physical changes or chemical reactions. Imagine you mix hot water with cold water. Heat will flow from the hotter water to the colder one until they reach the same temperature. A calorimeter, a well-insulated container, allows us to study this heat transfer in a controlled environment. By measuring the temperature changes of the substances involved, we can calculate the amount of heat exchanged. Calorimetry helps us understand how much heat is released or absorbed during various processes, from melting ice to burning fuel. Now let's dive deeper into the different types of thermal expansion. First up, we have linear expansion, which deals with changes in length. Imagine a metal rod heating up. As the temperature rises, the rod gets slightly longer. This change in length is directly proportional to the original length of the rod and the change in temperature. We can represent this relationship with a simple equation, dl equals sine AL dt. Here, dl is the change in length, L is the original length, dt is the change in temperature, and alpha is the coefficient of linear expansion. This coefficient is a material property, meaning different materials expand at different rates. Section 5 Area expansion. Growing in 2 dimensions, linear expansion was about 1 dimension, length. But what happens when we have a 2-dimensional object like a sheet of metal? That's where area expansion comes in. As the sheet heats up, it expands in both length and width. Similar to linear expansion, the change in area is proportional to the original area and the change in temperature. We can express this relationship with the equation, dA equals Bay dt. Here, dA is the change in area, A is the original area, dt is the change in temperature, and beta is the coefficient of area expansion. For most solids, the coefficient of area expansion is approximately twice the coefficient of linear expansion. Section 6. Volume expansion, expanding in all directions. Finally, let's talk about volume expansion, which applies to 3-dimensional objects. When a solid object like a cube heats up, it expands in all 3 dimensions, length, width, and height. The change in volume is proportional to the original volume and the change in temperature, as shown in the equation, dV equals gV dt. dV represents the change in volume, V is the original volume, dt is the change in temperature, and gamma is the coefficient of volume expansion. For most solids, the coefficient of volume expansion is approximately 3 times the coefficient of linear expansion.